Okay, welcome to another video. Today we're going to talk about terminal conditions for the simplex method. Essentially, where can you end up when you run the simplex method? Or linear programs in general can have four outcomes. You can have a unique optimal solution. You can have multiple optimal solutions that have the same objective value. It's possible that you'll end up with no feasible solutions, or it's possible that you end up with an unbounded objective. Okay, that is, you can make the objective as good and arbitrarily good. You can make it infinitely good without running into a constraint that prevents you from continuing to increase it. So infinite profit or something like that. So thinking about, here's a linear program in kind of matrix vector form for a maximization problem with less than or equal to constraints. Let's look at each of these three options visually, okay? And so when you look at the objective here, this C vector that we're essentially, as a row vector that we're multiplying with our variables, this C vector encodes the direction of the objective function, and that's the direction of steepest increase for the objective function. So if you have a constraint, like this one that I've kind of sketched out here, and you've got a C vector that's the direction of your objective, you can think about the simplex method will always move you along the boundaries of the constraints. And so you can think about projecting that C vector down onto the constraint, and it's either going to point you this way along the constraint, which means we'd want to move that direction, or if the C vector was more this way, then it would point you, the projection onto this constraint would move you this way along that constraint, okay? Key idea of the simplex method is that we're always moving along the boundary of the feasible region. And so we're always moving along those constraint boundaries. Okay, so here's the first option. We can have a unique optimal solution. And so here's the C vector, this one here. Here's two constraints, and we end up at a corner point of those two constraints. And if we think about projecting the C vector onto this constraint, we'd want to go this way along it, but the other constraint prevents us from moving any farther that way. Similarly, if we take our C vector and we project it down perpendicularly onto this constraint here, it says we'd want to move this way along the constraint, but then this constraint prevents us from moving any further in that direction. And so that's the scenario that you'll have when you end up with a unique optimal solution. Okay. Second possibility is that you have multiple optimal solutions. And so in that case, if we got our C vector here and it's perpendicular to the constraint boundary. If it happens that it's exactly perpendicular to the constraint boundary, then if we think about projecting onto that constraint, we wouldn't have a direction really going either way. And so actually, as we move along this constraint boundary here, all of those solutions have the same objective value. And so you get a corner point solution here, you get a corner point solution here, and actually everything in between them would also be an optimal solution. So if you get two optimal solutions, you're actually guaranteed to get infinitely many optimal solutions along the line in between the two optimal solutions. Okay. Third option is no feasible solutions. And so here's maybe one constraint pointing this way, another constraint pointing down this way, and a third one going up that way. And there's no region there that satisfies all three. If you sort of ignore this constraint, then this region over here would be feasible. But once you add this constraint in, it sort of eliminates that region there. And so no feasible solutions usually means that you have too many constraints or that the constraints are not consistent with each other to give you any feasible region. Okay. Fourth option is that you've got an unbounded objective. So in this case, our C vector maybe points this way, but we've got a constraint that's pointing us this way. And so really our feasible region is everything over here. And so if we're at this corner point, we can keep moving this way along here, and that's going to still be feasible, and it's going to keep improving our objective. And so Yeah, it's possible to have an unbounded feasible region and still have a unique optimal solution. But when the objective direction sort of points out towards infinity, then you're going to get an unbounded objective. If our uh, objective direction were to point in towards this boundary or down towards this corner or over towards this corner, we might have an optimal solution. But in this case, it's unbounded. And in this scenario, usually it means that we're missing some constraints. And so maybe we can imagine that we should have another constraint sort of laying in here like this that limits the amount of x1 and x2 if we're going to have an objective function that's sort of pointing out. Okay, so visually, that's the four scenarios that can happen. And you're guaranteed that if you run a simplex method on a linear program, you're going to end up in one of these four end cases. Let's talk a little bit about them kind of as you see them in the simplex method. So first case is unique optimal solution. This is what we've seen many examples of at this point in time. Anytime you run the simplex method and you end up with your non-basic variables are negative. So if the reduced cost, which are the values in the objective row for all your non-basic variables, are negative for a maximization or positive for a minimization problem, then you know you're at a unique optimal solution. Okay, that's our regular check for optimality. And if you pass it, then you have a unique optimal solution. If they are all negative for the non-basic variables, they'll be the reduced costs or the values in the objective row will be 0 for the basic variables. Okay. If you're using OMPR, if it finds an optimal solution, there's a status flag that you can check, and it will give you a message of success. And if you dig further into that results object and look into additional solver output, ROI, message, and status, it will give you a kind of cryptic code of 5. And that's GLPK's sort of code for solution is optimal. Okay. So that's a scenario that we've actually seen a couple of times, and so I won't work an example of that. The next possibility is multiple optimal solutions. In this case, we've got some non-basic variables, at least one non-basic variable that has 0 for its reduced cost. And then all other reduced costs are negative for a maximization problem or positive for a minimization problem. So in essence, we pass the optimality test, but at least one of our non-basic variables has 0 reduced cost. Now, when you have 0 reduced cost, it means that you can bring that variable into your basis without changing the objective value. So we have then a direction that we can move with our simplex method that neither increases nor decreases the value of z, our objective. Okay. So, and if we want to find the other optimal solutions, we do exactly that. We pivot and bring in that variable with 0 in the objective value row, and we pivot on that and bring that in. Okay, and that will find us our other optimal solutions. So here's an example. We've got x1 plus 2x2 is our objective, and we want to maximize that such that x1 plus 2x2 is less than 10. Okay, this is probably a simple enough one. You can solve this one in your head for what the optimal solutions are going to be. But let's actually put it in the simplex method. And so here's our initial tableau. We look for negatives in the objective row. And so let's choose x2 as our entering basic variable. If we do that pivot, we'll divide this row. Well, first we'll check our ratio test and we'll get 5. And then so we only have one row. It passes the ratio test. And so we'll use it as our pivot row. So we'll multiply this row through by 1/2 and get this, and then we'll kind of zero this entry out here by adding this row and this row together, and that will get us to this next tableau. Looking at this next tableau, x2 is now our basic variable, but if we look at x1, it's a non-basic variable, but it's got 0 in the objective row, okay? Our other non-basic variable, S1, has a positive number in the objective row. And so S1 will not improve the objective, but X1 won't change it. Okay, so let's bring X1 into our basis. And so we can pivot on this column. And if we check our one row, we get a ratio test of 10. And so we'll multiply this row through by 2, and we'll get to here. And so we've got two solutions. This first solution we can read off as X2 equals 5, X1 and S1 are both equal to 0, and we'll get an objective value of 10. The second solution that comes from here with X1 in our basis will give us that X1 equals 10, X2 and S1 are equal to 0, and Z is equal to 10. So both of these have the same objective value, but they're two different solutions. And if we look at this visually, here's our constraint, and our direction for our objective vector is actually exactly perpendicular to that constraint. And so here's our first optimal solution that we found. Here's our second optimal solution that we found. And actually everything in between there along that constraint also ends up being an optimal solution for this problem. Okay, so moral of the story, you get multiple optimal solutions if you have at least one 0 reduced cost in that objective row once you get to the point where you'd otherwise be optimal. Okay, if you're running OMPR, the solver will give a status of success. And if you dig into that additional solver output, you'll get a message status that is code 5, which is also solution is optimal. And so you'll notice you get the same code 5 and success, whether there is one optimal solution or multiple optimal solutions. So in that sense, OMPR is kind of unhelpful at letting you know whether there's one optimal solution or more than one optimal solution. But I will say there is a way to know the difference, and we'll discuss that when we dive into sensitivity. If we look at some of the other output that the solver gives us and look at essentially the solver can tell us what these reduced costs are. And we'll dig into that next week when we talk about sensitivity. And so by looking at those reduced costs, then we can know whether there are multiple optimal solutions. So let's move on to the next scenario, which is no feasible solutions. We saw this before when we were using the big M method. We have no feasible solutions if the big M method reaches an optimal solution to the relaxed problem where we added the artificial variables, but we've got non-zero values for those artificial variables. Those artificial variables encode how much we're violating the constraints, and if we have non-zero values for them, then we're still violating the constraints. And if there's no direction that we can move to improve on that, then we're at a point where we're have no feasible solutions. Okay, this often means that your problem's over constrained and you have too many constraints. Okay, or just that what you're trying to do is not possible as well. That might be something where your boss says we want this, and this, and you try to code it up, and you have to go back to your boss and say, well, which of those are you willing to give up because we can't do all of them? So in OMPR, the status flag will give you a status of error. And if you dig into the additional solver output, you'll get a status code of 4, which GLPK defines to be as no feasible solutions. Okay. So yeah, we've seen an example of no feasible solutions for the simplex method before, so I won't work an example of that. Let's move on to an unbounded objective problem. Okay, so in this case, if you have an unbounded objective, then you're going to have a direction or an entering basic variable that you can bring into your basis, which satisfies what you want for either a minimization or a maximization problem. But there's no exiting basic variable. Okay, this happens when all the potential pivots in the column of your entering basic variable are either 0 or negative. Okay, you can't pivot on a row with a negative or 0 pivot. And so there's really nowhere to go there. This means that your objective value can be improved arbitrarily large by bringing that variable into the basis, but you're never going to run into another constraint is really what's happening here. Okay. This usually means that you're missing a constraint from your formulation. So let's see an example. So here we've got x1 plus 2x2 subject to the constraint that x1 plus x2 is greater than or equal to 10. Okay, visually we've got a constraint looking this way, and we want to maximize something that's also sort of pointing out this way. And so, yeah, our objective function, sort of C, is pointing this way. We'd have to introduce an artificial variable S1 bar. So S1 is going to be our surplus variable. S1 bar is going to be our artificial variable. Here's our setup, putting it in a tableau. We have to do that kind of half step initially to make it so that S1 bar is our basis variable and eliminate this M here. So we multiply this row by negative M and add it up. That'll get us to our actual starting tableau here with a solution S1 bar equals 10. X1, X2, and S1 are all non-basic variables, so they're 0. And at this point, Z is negative 10 times a huge number, so like negative 10 million. Okay, so then we can look, we're trying to maximize, so we choose a negative reduced cost in our objective row for our pivot. You could choose either x1 or x2 as your entering basic variable. I'll go ahead and choose an x2, and we can pivot on that. We don't have to multiply this row by anything, but we'll need to add m plus 2 times this row added up to that to turn that into 0. When you do that, you'll end up with this tableau. And if we look at this tableau now, x2 is equal to 10, x1 and S1 bar are all equal to 0 because they're non-basic variables. And so our artificial variable has left our basis. And so now we're in a feasible solution. And now our Z value is 20. Okay, and so we went from negative 10 million to 20, huge improvement in our objective, right? We've gotten rid of all the penalty terms. Now, if we try to look at this tableau and ask where do we go next, we'll notice that S1 has a negative reduced cost, which means that we can select S1 as our entering basic variable. And then we look at that column and we want to do our pivot. And as we try to do the ratio test, we only have negative values in that column. Okay, there's only one row, so really just the one negative is enough. But if you were to have more rows, you'd want to check that all of them are negative. And it means that essentially we can increase S1 as much as we want, and we'll never drive X2, which is our current basic variable, to 0. And so if we actually look at what this constraint says, it says that x1 plus x2 minus s1 plus s1 bar equals 10. And x1 and s1 bar are going to stay in non-basic, and so we can kind of cross them out and ignore them. X2 is our current basic variable, whose current value is 10. S1 is currently 0, but we'd like to make it non-zero and increase it and bring it into the basis. And so if we move that over to the other side, we get this equation here that x2 is equal to 10 plus s1. If we start increasing s1 from 0, x2 is not actually driven to 0. Okay, it actually just keeps getting bigger and bigger as well with s1. And so a negative here kind of comes to a negative here. When we move it to the other side, becomes a positive. And so increasing our entering basic variable actually makes x2 bigger instead of smaller. It never drives it to 0. Okay, which means that we never run into another boundary of another constraint, is the way you want to think about that. And sort of visually here, we started at 0, 0. One step here, we're now up on this constraint and we're in now the feasible region. And then if we were to try to do another step where we start increasing S1 and going away from this constraint here, X2 would also be increasing and we'd just be going off to infinity and continuing to improve our objective. So that's what happens when you have an unbounded objective. It's usually because you're missing some limited resource that would actually prevent you from going off to infinity. Very rare that anything can be infinite in this world, right? So we don't have infinite resources. And so if you have an unbounded objective, it's usually because you've forgotten to include some limiting resource in your constraints. So in R, if you're running a problem with this, GLP with OMPR, the status flag will result in error as well. Okay, so it says this is an error, even though there's solutions, there's feasible solutions. It tells you an error because essentially you can go off to infinity. And if you dig into the additional solver output, it'll give you a code equals 6, which GLPK defines as solution is unbounded. So there's 4 codes. 4 and 6 are error codes. 4 is no feasible solution. 6 is unbounded. 5 for GLPK is that the solution is optimal. Okay. Most linear programming solvers use this kind of pattern of using codes to indicate the exit status, but they're not at all consistent across different solvers. And so for the GLPK solver, at least, 4 is no feasible solutions, 5 is optimal solution, and 6 is solution is unbounded. So here, let me quick show you what this looks like in R. So here's a small program that I made that has a unique optimal solution. If I run this and then I look at the results, which is what I got from the solve command. If I look at the results and status, it'll give me status equals success. And if I look at those same results and look into the additional solver output, I'll get code equals 5. For multiple optimal solutions, I'll get the same status of success and the same additional solver output of status equals 5. If I've got a problem with no feasible solutions, I'll get status equals error. And then for additional status, I'll get 4. And then when there's unbounded objective, I'll get error for status and the extra status being 6. So an example of what you'd see using the OMPR package in R. That's it for this video.